Okay, thank you, Paul. So today I will continue my talk of yesterday. I will start with the spectrum of the S-clique extension of a square grid. Yesterday could not be seen what it was exactly, but it is what it is here. Yes, and then using the Hofmann polynomial, we obtain this equation. It is not so difficult to see, and this implies that if you look at the third power of the isolation matrix and you look at the xy entry, and you have these three expressions. The first one is x is equal to y, the second one is x is isolated to y, and the third one is x is not isolated to y and x is not equal to y. And lambda xy is the number of common neighbors if they are associations, and mu if they, and we have seen a Hofmann bound, so I'm not going to talk about this today. So now let's get really started. So from now on, we look at this kind of co-Atelier graph with this spectrum. This is the S-clique extension of the t+1 times t+1 grid that has this spectrum. And we want to show that it is really the S-clique extension of t+1 times t+1 clique extension. So you can see that the phase is s times 2t+1 minus 1. And I write its usual k, and its parameter as a co-S regular graph is the c is 2s. And this is not so difficult to see. You calculate from the a to the power 3, you look at the xs coordinate, and you know the number of edges in the local graph. And if you know the local edges in the local graph, you know how many edges there are between the local graph and the second subconstituent. Then you can count this in two with double counter. You can count this in two different ways. Then you get that every c is 2s, and then you get it that it is c is 2s because it's constant. For vertex infinity, let gamma x be the local graph of gamma at infinity. So we now look at from this graph the local graph. We need to look at that graph, the local graph. We're going to find big cliques in gamma infinity. We call them lines because I don't know a better word for them. They may intersect more than one vertex, but what else can I call them? If somebody has a better name, please tell me. Maybe I could call them cliques or something like that, but that is okay. That is not what I like, but okay. So we let D1, D2, dk be the phases of the local graph in the local graph. So if you like, is it lambda infinity x, if you like that better. You also write instead of dx for the phase of x of gamma infinity. Okay, here I made a mistake, sorry. That must be gamma infinity. Yes, the local graph, infinity is still infinity. So we can also see that because gamma is walk regular and co-S regular, we obtain that the number of walks of length 2 inside gamma infinity is the same as in the local graph of the S-clique extension of t+1 times t+1 grid. This makes to calculate it is much easier to do this way. Otherwise, you have to do with your. It can also done directly from the spectrum, but I prefer to do this way. It's for me easier. This implies the sum of the phases and the sum of the square of phases of the vertices in gamma infinity are constant and are given by the following two equations, where epsilon is the number of edges inside gamma infinity. So these are the two expressions. If you look at the sum of the degrees, that should be 2 times epsilon. And that is this expression. You see that it is, whatever it is exactly, this is an expression in S and T. And the other expression is, if you want to count the path of length 2 in the local graph, you only have to look at the vertex and look at the two neighbors of vertex. That is how you can look at from two ways. If you look at the middle vertex of that part of length 2, then you get the expression as I show here below. So we are going to use this, and as a consequence, we get this particular expression. The reason why we like this because it is this minimizes squares. If I look at the I minus constant, this is somehow this gives the smallest number of the right hand side is smallest for this particular. The rest says t squared times. Oh, I mean, here you see that this expression has s to the power 3 times t to the power 3. And this expression has t to the power 2 times s to the power 3. So this will make it easier. This is significantly smaller than that other expression. And we can all, the reason is that we look at this is that we want to prove that almost all vertices have degree about the st plus f, very close to that number. So we want to minimize to get that every vertex gets as close to this number as possible. So now we call a maximum Euclidean line if it contains at least 3/4 st plus 2. Now we're going to present a result that shows the existence of lines in gamma. So if you have co-S regular that is co-spectral with the S-clique extension of t plus 1 times t plus 1 grid, where co-spectrum means with the same spectrum, where S is at least 2 and t at least 1 are integers, then if t is 11 times s to the power 4, say, then any vertex in gamma lies on exactly 2 lines, not more and no less. It cannot be more than 2. That is easy because then the sum will be too large. So that is not possible. How do you prove this? I will only give the sketch of proof. I will not give all the details because some you have to calculate quite a bit. So now you know that the graph is irregular with physique k, and that is 2 times of s times t to 2 times t plus 1 minus 1. And co-S regular with constant c is 2s. And now you take infinity non-vertex of gamma, and gamma infinity is local graph at this vertex. And let epsilon be the number of edges inside gamma infinity. Then from the first equation, we got the sum of the degrees. We get that if s is at least 2, we get that this is lower bound. It's just the main term. That is what I really want to say here. This is just a simplification of that formula. There are some extra terms in there, but they are, if s is at least 2, that's at least 0. So now we derive an upper bound on epsilon. Of course, this upper bound must be larger than the lower bound. Let P be a co-clique with maximal order in gamma infinity with vertex set x1, x2 up to xp. Then P is the most s plus 1 squared by interlacing because the smallest eigenvalue of k1 t is minus square root of t. So that is the reason. Because the smallest eigenvalue of gamma satisfied that theta min of gamma is minus s minus. So we define the following set B, that are the vertices are changed to infinity with at least 2 neighbors in. Let B be the cardinality of B. B cannot be too large because it's 2s. So that means that B, it depends on which 2 neighbors it has. So that can be given to xi and xj. Then they can have at most 2s common neighbors inside the local 2s minus 1 common neighbors in the local graph, as x of infinity is one of their common neighbors. And so we get that B is at most 2s minus 1 times P choose 2. and P is at most S plus 1 squared. So you get that this is about S to the power 5. Now we define the sets AI, says that AI are the Y's, I say it to infinity, that has only X as a neighbor. And we also add Xi to this set. And we denote the cardinality of this set AI by small ai. This has nothing to do with the intersection numbers of the distance radial graph. There are no distance radial graphs here. Yes, we only look at a graph co-spectrum with the S-clique extension of t plus 1 times t plus 1. Note that any two vertices in AI are adjacent because P is maximal. Thus, for every I, AI is a clique in gamma infinity. Now, inside A, we must have at most this number of edges. Yes, because every AI has a most term. It's not so difficult to see. Yes, for every AI, you calculate how many edges there can be between the AIs. Inside B, because this is it is of order B, we have almost half B times B minus 1 edges. And between A and B, we don't know how much, but it is about B times K minus B. Yes, there are B. They can be associated to every element in B, A. Every element in B can be associated to every element in A. That is what this says. So we can add them up and maybe obtain that 2 epsilon is at most this expression. Then all the three together. And after some calculation, you find that it is about this AI times AI minus 1 plus some term which is S to the power 6 times T. So S is fixed and T can be very large. So that we have to think as a fixed number and T as a large number, much larger than S. That is how you have to think. Now you use that the AI sum up at most K. Yes, because that's clear that the AIs is the most K because we can only count that is less than AI, the sum of AI plus B's, and B can be more than equal to 0. That is what. If the vertex infinity is on only one line, we obtain a contradiction, as then the lower bound for 2 epsilon is larger. So that is, so now we found that every vertex lies on 2 lines. Every vertex of gamma lies on 2 lines. But the lines, what is the order of the lines? We don't know yet, yes? To show now that the 2 lines have the right order always, it's not so easy, but also not so hard. And if you know if this is regular, is a local graph of this regular, then it may make your life quite a bit easier to do this. But the first part you cannot, on this moment, you cannot change so much. And once you know that all the lines have the right size, then you know you have your S-clique extension of T times T plus 1 times T plus 1. So now we look at the Neumaier-Koolen. I'm sorry, I missed the I in Kupferstein, sorry. So now we know that each of the local graph is a Q-clique extension of the QD minus 1 over Q minus 1 times QD minus 1 over Q minus 1 grid. We finish the proof using the Neumaier-Koolen theorem. So this theorem is theorem 938 in BCN. For diameter 2, it was done by Neumaier and Kupferstein and Cohen, I think, generalized for any diameter. So now we want to have a connected graph such that the common neighbors of two vertices at distance. But sorry, here I make a lot of mistakes. The common neighbor of 2 vertices at distance 2 induce a grid. I'm sorry, there's too many mistakes here. I'm sorry for that. And the common neighbors of a co-clique XYZ. That means for every, they must be the common neighbors of x, y, and z, and then that we ask that subgraph to be a co-clique. Then the gamma is either a clique, a Johnson graph, a certain quotient of a Johnson graph. We still is same. We still locally is a grid, or a Grassmann graph. So this is the Neumaier-Kupferstein-Cohen theorem. Now we finish the proof for the characterization using the Neumaier-Kupferstein-Cohen theorem. So what do we need to do? So any local graph is a Q-clique extension of the Q minus 1, Q to the power D minus 1 over Q minus 1 times QD minus 1 over Q minus 1. That means that gamma does not contain an induced K13. So this co-clique of order 3 can never have a common neighbor. So it is empty. So therefore it is a co-clique by definition. An empty set is always a co-clique. So the second condition is satisfied. Now for the first, C2 is Q plus 1 squared, and the mu graph has phase C2Q. It's also a subgraph, an induced subgraph of the Q-clique extension of the Q to the power D minus 1 over Q minus 1 times QD to the power D minus 1 over Q minus 1 squared. So that means that every vertex in the mu graph lies in exactly 2 cliques. So it is a line graph, and hence the Q plus 1 times Q plus 1. So the first condition is satisfied. And yes, so now we can apply the Neumaier-Kupferstein-Cohen theorem. So now I will finish my talk by considering the bilinear forms graph, the build 2 DD. That means we look at CF2 and the bilinear forms of D by D that are matrices of D plus 3, and you look at D times D matrices over CF2, and you say that 2 of those matrices are adjacent if the difference of the 2 matrices has rank 1. So with Gavrilyuk, we show that the bilinear forms graph built to DD is characterized by its intersect numbers, and that is in this paper in Combinatorics 2019. The proof is fairly easy. The proof is not so easy, let's say so, because you still have the same problem as for Grassmann graphs 2DD, because you still have two blast cliques in the local graph. So you don't get that the graph, the geometricity, you cannot easily do the geometry of that is the geometric distance radial graph. You only get it after you have shown that it is the bilinear form graph. Then you get that the graph is geometric. Because beforehand you don't know whether you can split the delta cliques in 2 sets of geometric delta cliques. The 2 sets of geometric delta cliques. You don't know that. And how do you do this? The local graph must have the same spectrum as a square grid. Because in this case, you have again a double root as for the Terwilliger polynomial, and the eigenvalues must lie either is that positive eigenvalue is either A1, this positive eigenvalue, or it lies between -1 and -3. Then we're using an elementary number theory. You can see that because the eigenvalues must be algebraic integers, that means that all the eigenvalues inside the -1, -2, the -3, -3, -1 interval must be integers. It must be -3, -2, and -1. Once you have this, you can calculate the multiplicity of these 3 numbers. And then it turns out that the -1 and -3 have multiplicity 0, and -2 has so then you get that it is a line graph, and then must be by the numbers, looking by the numbers, you see that it must be the square grid, because it must be a stronger radial graph. Yes, because it had only 3 distinct eigenvalues. The local graph is K regular, and it's a A1 regular and has 3 distinct eigenvalues, so it must be a stronger regular graph. Then you show that the mu graph must be a 6th one. This is easy. The reason that this is easy because the C2 of those graphs is 6, and the C of the square grid is 2, so it must be 2 regular graphs. You have to have a 2 regular graph on 6 vertices. There are only 2 graphs like that. Yes, that is 2 times triangles, 2 triangles, or the 6th one. And it's fairly easy to see that the 2 triangles cannot occur, so it must be 6th one. And then we apply a theorem by Munoz and Spektorov, and then we are done. For Q bigger than 2, we could not determine the spectrum of the local graph. If for Q equal to 3, there were too many possibilities. So because you don't have this reasoning, but there are not so many possibilities for Q is 3, but there are too many. Maybe it can be done. I don't know, but we don't know how to do it. Maybe somebody can look at it and see whether it's possible. But we didn't see it. That's possible if for Q is 3. And this is the end of my course. Thank you for your attention for this week. And I can hear you, but what did you say?
What? All I said. So the local graph for Q bigger than 2. So you look at the local, the neighbors of the zero matrix, and so you just
yes.
make the form UP transpose. Why is Q equal 2 so nice and Q equal 3 so hard?
I cannot hear your question exactly.
You want the eigenvalues of the local graph. Can you hear me now?
Now I can hear you clearly.
So I'm asking about the difference between Q equal 2 and Q equal 3.
Because in Q is 2, you get -1, -2, and -3. For Q is 3, you get many more possibilities for your eigenvalues.
But you still just have the matrices, the rank 1 matrices, right, as your vertices, and you're checking the differences.
I agree. This must. But you only have the parameters of your graph, not that it is a bilinear forms graph.
Oh, okay. So you're not saying that the local graph of the bilinear forms graph is hard to work out. It's hard to work out what could
have
happen.
a graph with the same parameters as a bilinear forms graph with Q is 3. Then, then you have too many possibilities.
But in the case of the bilinear forms graph, are the eigenvalues very well controlled?
Yeah, of course. They are also S-cliques extensions of grid graphs.
Oh, they're S-clique extensions. Okay.
That is a very easy kind of graphs. Yeah, but to prove that they are the graphs, that I don't know how to do that.
Okay, thank you.
Do you happen to know off the top of your head what the naive range is for Q equals 3? So for Q equals 2,
I mean, for Q is 3, as you know, that's then the intervals are most 3, so have length 3, so they are all this two cosines a kind of eigenvalues. Yes.
Yeah.
But I don't know. That must be a very fine number, but not 3, as in the case for if you have only -1 and -3. Yes.
Yeah. Thanks.
You probably know better than me. Let's say so.
Question
yes.
about the Grassmann graphs, J, Q, and D, where the N is 2D plus 1. Okay, now we have the actual Grassmann graph, and then we have these the pseudo one.
Yes.
Okay, now is there any classification? Could there be a third type of distance regular graph with the same intersection numbers that's neither the?
I'm very surprised.
But is that open?
There's no reason why they would not exist on this moment. There is no real reason why they should not exist, as far as I know. But I would be.
I was surprised to begin with when the second family was discovered,
including ourselves.
So what about diameter 2 Grassmann graphs? Are there,
That is
impossible?
certain, that is a certain kind of designs, and those designs, they exist too many of them. So there's no hope at all for Daimler to, there is any hope.
let's discuss the Grassmann graphs J, Q, and D, where N is 2D. So this one. that
Yes.
you- Okay, so so could you just review what does the classification say? For all values of Q and D?
For essentially for Q at least 2 and for D at least 9, they must be the Grassmann graphs.
Okay, D at least 9.
Probably you can, I mean, for Q is 2, maybe you can, for Q large, say at least 6 or at least 7. I think that the D is the most, at least 6 is enough, but I don't know the exact numbers on this moment. But I think they can be improved, but I would be very surprised if there were any other graphs, even for diameter at least 3.
I think Munamasa has his hand up.
I have a question.
Yes.
Jeff, can you hear me? Jeff, can you hear me? Yeah,
Yes,
I have
I
a
can.
question. Yeah. So my question, at some point you mentioned there is no K13 in the graph when the local graph is a S-clique extension of
And the
T
local
plus
graph,
one.
so what I meant really in the local graph, there's no K13.
Oh,
That is
local,
what-
not in the gamma. Okay.
Yeah, that
Thank
means that is what you need. Yes, that is what you need to show that this is an.
Yeah.
I made a mistake here. I'm sorry. Yes,
No
I meant
problem.
to say in the local graph you don't have K13.
Yeah.
Then you get the co-clique. Yes.
Yeah, thanks. And maybe another silly question that you mentioned my result with spectra at the end.
Yes.
How does that come into play? Maybe I missed the point. That was a characterization of alternating forms graph.
Yeah, but I think the Gavrilyuk took your classification and generalized it to the bilinear forms graphs.
Uh-huh.
So you do it is you look at local grid graphs where the mu graph is an hexagon.
Mm-hmm.
That is what he did.
Mm.
This is part of the work.
Yeah, thank you very much.
And good night, everybody.